the class NP with access to a SAT oracle. Sigma 2 is equal to NP with access to a SAT oracle, right? So let's see how we'll see that. We'll see the detailed proof. And in general, what is true is that sigma I is NP with access to a QSAT I oracle. So you may recall that QSAT I was the complete problem in the complete problem of the sigma I, right? So QSAT I is the QSAT K was the complete problem of sigma K. So QSAT 2 is like there are these alternating quantifiers. Similarly, I'm just trying to see if I defined it. I think I just defined it to be similar to QSAT 2, but QSAT I is a complete problem for the class sigma I. So sigma I plus 1 is NP with access to a QSAT I oracle. So basically, if you have, it is NP with access to the complete problem of the class just one level below. So here it's sigma I plus 1. Here it's sigma I plus 1. For that we need NP with access to sigma I complete language. And similarly, pi I is co-NP with access to a QSAT I complete problem, right? QSAT I, which is sigma I complete problem. Okay, so this is so these results, the proof of these results are exactly like the same way that we will see the proof of sigma 2 is NP-SAT. So because of which we will not really be doing the other proofs, we'll just show the proof that sigma 2 is NP with access to a SAT oracle. Okay, so like I said in the lecture 23, the previous lecture, whenever we want to show something like A language or class A is equal to class B, we end up showing containment in both directions. So we'll show that left hand side is contained in the right hand side and vice versa. So like that, we will let us do first direction, that sigma 2p is contained in NP with access to a SAT oracle, right? So which is what we have here. So, and again, how do we show that one set is contained inside the other? Again, the standard trick is to pick an arbitrary element of the first set. So in this case sigma 2. So let L be a language in sigma 2. And now we will show that this L is in NP with access to a SAT oracle. So an arbitrary member here, if we can show it to be there, then it means that any member here is there, and so this is a subset of that. So we will take L to be in sigma 2. So what does it mean when I say that L is in sigma 2? When I say L is in sigma 2, this means that L has there is a deterministic polynomial time verifier V, such that whenever X is in L, there are strings Y, or there exists a string Y, okay, such that for all Z, the verifier evaluates X, Y, Z to 1. Again, there are other things about Y and Z being of polynomial length. I am just skipped that detail. So this is the definition of sigma 2. L is in sigma 2 if there is a polynomial time verifier V such that for all X in L, it must be the case that there is a Y such that for all Z, V X Y Z evaluates to 1, right? Or the deterministic verifier successfully verifies X, Y and Z. Okay, so now consider such an L. Now we need to show that such an L is also there in NP with access to a SAT oracle. So what can that, so basically we have to construct the NP machine, the non-deterministic Turing machine, non-deterministic polynomial time Turing machine with access to a SAT oracle, right? So let's see how to do that. Okay, so the non-deterministic Turing machine, so basically given input X, it can guess the Y, right? It can guess this Y, which is because NP has a capability to guess, but NP cannot do this for all Z thing, right? So NP cannot do that because NP can only guess something if it is there, right? So basically, given input X, it can guess Y, and now once X and Y are fixed, then it needs to decide if this is true. What is true? For all z, is vxyz equal to 1, or does the verifier accept the triplet xyz? And slight notation change may help to change the perspective and view things differently. So once x and y are fixed, right? So x is the input and y is the guessed. Once y is guessed, now vxyz is just a function of z, right? So one thing that we can do is to bring down x and y as a subscript and then view it as a function of z alone. So once x and y are fixed, we can view vxyz as a function of z alone, which is what is happening here. Function of z alone. So now the NP machine needs to decide. Again, notice that till now we have not made use of the SAT oracle. NP machine needs to decide whether for all z vxyz is equal to 1, which is the same as we defined vxyz to be this, right? Vxy with vxy as subscript of z, right? And so what is the negation of this? The negation is there exists z such that vxyz equal to 0, right? For all z, v is equal to 1, and the negation is that there is some z for which it is 0, right? For all z something happens, for one z it does not happen, right? That's the negation. So negation is there exists z for which vxyz is 0. Now instead of vx, I can change the verifier, right? I can modify the verifier to give another polynomial time verifier which just flips the output. So I will define a new verifier called v prime xy, and v prime xy is just flip the output of vxy, right? So you just let vxy run and you flip the output. So it's just a flip. So vxy equal to 0 means v prime xy equal to 1. That is what we have in this red circled input. So we want the negation of this, right? So is the opposite of this true is what we want to know. But does there exist a z such that v prime xy is v prime of z is equal to 1? It's just a satisfiability query, right? So you have a verifier which can be viewed as a formula also, right? So the entire verifier is an algorithm which, like in Cook-Levin theorem, you can view it as a formula, and you are asking whether there is a z that satisfies it, right? You are asking whether there is a z that satisfies it. If there is a z that satisfies it, so that is a satisfiability query. So you can ask the satisfiability query, and what we want is a negation of that. So the negation is just you flip the output again. So all that it boils down to is a negation query, right? So that is what we need to do here. It's a negation query. It's a negation of a satisfiability query. So just once again, we need to have given a language in sigma 2, we need to view it as we need to see how it is NP with access to SAT oracle. So sigma 2 means it can be written in this form with the polynomial time verifier v. There exists y such that for all z vxy equals z equal to 1. So then npm n can guess y, and it needs to decide for all z vxy z equal to 1. So instead of doing that, we realize that we can view it as a satisfiability query. Does there exist a z that such that something happens? And that can be easily be done because we have access to a SAT oracle. So we just make the query to the SAT oracle and then decide accordingly, right? So that's why sigma 2 is contained in NP with access to SAT oracle. So that is just one direction of the proof. The other direction is pending. What is the other direction? That NP with access to SAT oracle is contained in sigma 2. So again the same thing. We take an arbitrary language from the left hand side, which is NP with access to a SAT oracle. So which means L is decided by a non-deterministic polynomial time machine N with an oracle access to satisfiability. Right. So this direction is slightly more involved than the other direction. So let me just go a bit slow. So what can N possibly do? N is a non-deterministic Turing machine, so which means it has possibly multiple computation paths, multiple accept rejects outcomes, and it also has access to a SAT oracle, which means it will query the SAT oracle from time to time, right? It can query the SAT oracle from time to time, and it can also use this in an adaptive manner, right? So it can make a query, and then if the response is yes, then it does something. If the response is no, all this is part of the algorithm. So these are the things that N is capable of doing. So it's a non-deterministic machine, not NP with access to a SAT oracle. Right? Suppose, so just to summarize, or just to say it very, very formally, suppose X is in L, that means it's a non-deterministic machine. So that means there is one sequence of choices that leads to X being accepted, right? Because it is non-determinism. So let these choices be C1 to Cm. It will be a fixed number of choices for a fixed input, right? So let it make M choices by the non-deterministic Turing machine N, okay? And in this process, right? So these process will guide it using some computation paths. So it has access to the SAT oracle. So it may be making many queries to the SAT oracle. So let us say it makes k queries, where k is another fixed number. K queries to the SAT oracle. Let the responses to the k queries be A1 to AK. Okay, these are all yes/no responses. Equivalently, we will view them as 0/1 responses. Okay, this is a yes instance, this is a no instance, right? Okay, so for each of the queries, it receives AI as a response, right? Okay. So what it does is, so I'm just trying to represent what it does in a pictorial fashion. So it makes many choices. C1 to Cm, and queries it makes queries phi 1, phi 2, etc., phi k. So I said it makes k queries. So, and recall, each of them is a instance of satisfiability, because that is the oracle that we have. So let the queries, so every time it must be writing a SAT instance, which is what is a SAT instance? It's a Boolean formula. Let the query, so the Boolean formula instance, let it be phi 1, phi 2, phi 3 up to phi k, right? And the answers are A1, A2 up to AK. Right? K queries, K answers. And if X is in L, there is a sequence of choices C1 to Cm such that which makes some K queries, and which makes some corresponding to the queries, you get the correct answer. So again, the queries are fixed by the choices, and the answers are decided by the queries, right? It's a yes instance or no instance, is the oracle doesn't lie, so it just gives the correct answer, right? So this is what happens. And so again, this is just what I written here. Phi I denote the ith query, right? So if the answer is 1, which means it is satisfiable, phi I is satisfiable, which means that there is a satisfying assignment for phi 1. Let us call it U1, right? So U1 is a satisfying assignment for phi 1, which means phi I said U1, it's Ui. So phi I, when given the assignment Ui, it is it evaluates it true or 1. If AI is 0, right, if AI is 0, which means it is not satisfiable, which means there is no satisfying assignment, which means whatever assignment you try, whatever assignment Vi you try, for all assignments Vi, phi I of Vi will be 0. Right? So whatever you input, it will be 0. Again, what was the goal here? The goal here was to show that L is in sigma 2. Right? We started by saying L is in NP with access to stat oracle, which means it makes non-deterministic choices and gets yes-no answers, right? And we are trying to interpret what these yes-no answers are, right? So if it's yes answer, there is a satisfying assignment to the query. If it's a no answer, there is no satisfying assignment to the query, and that's where we are now. Now, all that we need to do now, so till now it seems like we were just understanding what it means for this language L to accept a string X, right? It needs to have a sequence of choices and then queries and then yes and no and all that. Now, all that we need to do is to write these things in a formal logical sense, and that will start looking like a sigma 2 language already. So let us see. So all I'm doing is to just write it very formally in a logical sense. So if X is in L, right, or X is in L if and only if there exists choices C1 to Cm, right, some m, some fixed number, responses A1 to AK, right. So the choices guide the machine to make queries, and obviously there will be answers, right, which lead to acceptance. So but then we are also encoding acceptance here, and U1 to UK can be, there are U1 to UK satisfying assignments for the cases where this is important when AI equal to 1, right? So UI is, so phi I UI equal to 1 when AI equal to 1, right? And such that and there exists a UI, right? So that's why it is all of these three things are coming under the existential quantifier. So I'll put a bracket, and this thing for all, we should be for all, because if AI is 0, then whatever input you try should not work. So this V should be for all quantifier. So we have a there exists quantifier and we have a for all quantifier, right? And such that N accepts X using choices C1 to Cm and answers A1 to AK, and right. So this is the choices of this is acceptance of N, and finally we also want to verify the correctness of the queries. Okay, so this is just about N. We also want to verify what the oracle did, right? So that also we should be doing. What is it that we should verify? So whatever I had written here, if AI equal to 1, then we should verify that phi I UI is equal to 1, right? So it's an implication that I have written here, but as we have seen in previous lecture, an implication can easily be converted to a Boolean formula. And if AI is 0, then phi I Vi should be 0. Anyway, for the Vi there is an external universal quantifier, so that will make sure that this applies for all the Vi's. And this we have to take an AND over all the choices of I. So in the two parts, either the left side or the right side may get active depending on what AI is. So there is an existential quantifier followed by a universal quantifier and followed by this formula at the bottom, and we have this part also, this light blue part, but this light blue part is also it's just a non-deterministic, it's just N accepts X using the choices M. So all this is something that is verifiable in polynomial time, right? So given M choices, it's just a matter of verifying whether this non-deterministic choices lead to acceptance. And what I've written in the bottom, this part also, it is easy to verify by a deterministic polynomial time machine. So the entire thing is a deterministic verifier with preceded by an existential and a universal quantifier. So that is the proof that an arbitrary language in NP with access to a SAT oracle is contained in sigma 2p. So basically we write down what it means for a language to be contained in NP with access to a SAT oracle. Once we write that down, basically it's a bunch of non-deterministic choices with a bunch of queries and responses. Once we write that down, we can encode it in a way with existential universal quantifier followed by a deterministic polynomial time verifier. And that's about it. That shows that NP with access to SAT oracle is contained in sigma 2p, and we have already seen the other direction. So this shows that sigma 2 is equal to NP with access to SAT oracle. And the other things that I said earlier, sigma I plus 1 is equal to NP with access to QSAT I oracle, and likewise for pi I plus 1. The proof follows very, very similarly. So I will not get into that. And one thing that you may wish to note here is that no, I think that's so. I was just trying to see if the quantifiers could be alternated, but it is not possible here because the choices have to be made before V1 to Vk, so you cannot alternate the quantifiers. And with that, we have completed the description of how we can get the languages in polynomial hierarchy using the Oracle Turing machine description. Now let me just summarize what we have seen in this week 4, right? We saw 4 or 5 different items. The first thing that we saw was p-space completeness. So we saw what is p-space, what is p-space completeness. We saw the language TQBF. And one point I felt I did not stress enough during the p-space lecture was that all of polynomial hierarchy is contained in p-space, because the QSAT k, which is the complete language for sigma k, is can be viewed as an instance of TQBF. Hence, all of the complete languages of all the classes in the polynomial hierarchy can all be reduced to the complete language can all be reduced to TQBF, which is p-space complete, right? So that is one point, p-space completeness and the fact that all of polynomial hierarchy is contained in p-space. We saw many instances of how games or the generalized instances of specific games such as chess are mostly p-space complete, because basically the game just boils down to analyzing a position, drawing the game tree, and at the end deciding a winner or loser is basically just you can encode it in a Boolean formula. So it just becomes like a fully quantified Boolean formula, and hence it becomes a TQBF instance. That is the reason why the generalized versions of games are p-space complete. Again, the finite versions of games are all finite, and then there is either a yes or a no or whatever answer, right? Like tic-tac-toe. After this, we saw Ladner's theorem, which stated the existence of NP intermediate languages if P is not equal to NP. Right? So NP intermediate is a space between NP complete and polynomial time. So it says that such a space exists if P and NP are different. It cannot be that P is there, NP complete is there, and there is a void in between. The space in between is filled with languages. And finally, we saw Oracle Turing machines. We saw the definition. And we saw the Turing reduction, and we saw how polynomial hierarchy, that like classes in polynomial hierarchy can be characterized as a result of the Oracle Turing machines. And yeah, and one more point is that, okay, one point that I missed, maybe I'll just add in the middle. Sorry, one point that I missed in the summary. Sorry. One point that I missed in the summary, which I will include now, is space hierarchy theorem. Basically, if f1 is, or if f is, or g is little o of f, then d space of g is strictly contained in d space of f, meaning there is something that you can compute with f space that you cannot compute with g space. This is space hierarchy theorem. Okay, this was proved also using diagonalization, much like time hierarchy theorem. So these were the main concepts. And with space hierarchy theorem and p-space completeness, space complexity, space bounded complexity part is complete. Now we are venturing into other aspects such as Ladner's theorem and Oracle Turing machines. Till space hierarchy theorem, or still space complexity, I was referring to Sipser. Now I don't think Sipser contains many of us. I think it may contain some of these topics, but I think it is better to refer to Arora Barak or Papadimitriou's book for the remaining topics. Or you can also Google it. There are many other lecture notes, excellent lecture notes where people have exposited on this. Of course, I will also share whatever I have been preparing. But in addition to that, you can also search for other material. And if you want other specific, if there are specific requests for other specific material, please feel free to write to me in the forum. I'll be happy to share. Okay. And with that, I'll conclude this lecture and conclude week 4 as well. Thank you, and see you next week.
Swayam Prabha, Digital India, Educated India.
Hello and welcome to lecture 25 of the course Computational Complexity. Today we are going to see an interesting theorem called the Baker-Gill Soloway theorem. So Baker, Gill and Soloway proved it in 1975. So let's first describe the motivation and then I'll state the theorem, right? The thing is that we have seen time hierarchy theorem, space hierarchy theorem, right? So the undecidability of the halting problem, all of this were proved using diagonalization. And most diagonalization proofs relativize. So what do I mean by relativize? Is that they can be extended to a setting where the Turing machines use oracles as well, right? In other words, if there is a proof that shows that a complexity class is strictly contained in another complexity class, right? Let's say C1 is subset but not equal to C2, right? Then the same proof can be extended to show that C1 with the oracle A is subset but not equal to C2 to the oracle A for any oracle A, right? So again, this is very important. So this will be true for any oracle that you choose. Because I'll explain the reasons below, right? Because the thing is that proofs that use diagonalization, basically relies on two things. One is that we need to be able to encode the Turing machine into some strings, right? So we usually say things like given the description of a Turing machine M, then you run the Turing machine M on its own description and then flip the output, right? This is what you typically do in the case of diagonalization. And then this will be part of a description of a Turing machine, let's say called it D, right? So D may have other things. And then you ask questions like what happens when D is fed its own description, and then you arrive at a contradiction, right? This is how proofs involved in diagonalization work. Halting problem, space hierarchy, everything, right? There are some other things like how much time, how much space, then you curtail it, truncate it, and so on, right? So basically, it relies on the notion of interpreting or encoding a Turing machine as a string and reading a string as both the description of a Turing machine as well as the input to the above mentioned Turing machine or to some Turing machine, right? And the second thing that proofs using diagonalization need is the capability to simulate one Turing machine using another Turing machine. So the proofs have things like, again, what I just said. We say things like you run M on its own description. So basically the Turing machine that we have, I earlier called it D. So D should be able to run M for any M, right? So if M1 is given, it should be able to run M1. So basically the Turing machine D has to have the capability of simulating any other Turing machine, right? So both of these are required and essential for a diagonalization proof. And both of these can well be extended to Oracle Turing machines as well, because if you can simulate a Turing machine, then you can also simulate an Oracle Turing machine, right? Because the only new thing that we have for an Oracle Turing machine is the fact that there are some Oracle calls to be made. So now Oracle calls is like checking the membership, and this part can also be included in the simulation, right? Checking the membership and then answering yes or no. Again, if necessary, it can be done by the simulating machine as well. Second is the encoding of Turing machine into strings. Again, this can be also done for Oracle Turing machines, because as I described in one of the previous lectures, Oracle Turing machines are just like any other Turing machines, but they have three special states: Q query, Q yes, Q no, and then an extra tape. So it is fits well within the framework of any other Turing machine. So you can have a similar encoding, and it can be interpreted by another Turing machine. So both of these encoding as well as simulation can be done for the Oracle Turing machines. So consequently, any proof that uses diagonalization, you could just mildly tweak the Turing machines involved in those proofs and get a proof for the relativized version of the classes as well. So if there is a proof that says a complexity class C1 is contained in complexity class C2, you can use the same using diagonalization. You can use the same proof to show that C1 to the oracle A is contained in C2 to the oracle A. If it says that C1 is not contained in C2, then again same proof works to show that C1 to the A is not contained in C2 to the A. So whatever you say between C1 and C2, it relativizes, meaning it can be said for C1 to the A and C2 to the A, right? This is what relativization means, right? This holds because both of these A and B, encoding and simulation, can be hold even for Oracle Turing machines, right? So this is the property of relativization. Relativization means even upon modifying the Turing machine to include oracles, the statements should hold good. So what this means is that, so let's try to understand the consequences. So one may wonder, like, because we saw P versus because we saw time hierarchy, space hierarchy, etc., undecidability, right, which seem to be big problems in the case of computability theory. So now, can one possibly solve P versus NP using diagonalization? It's a very natural question that somebody may ask. Can we use some diagonalization technique, very smart, very creative, to show that P is equal to NP or P is not equal to NP? Right? So one thing to note is that because of the relativization thing that we just noted, if there is a proof that P is equal to NP, suppose P is equal to NP, if there is a proof that uses diagonalization to show that P is equal to NP, then the same proof should extend or should relativize to show that P to the A is equal to NP to the A for any oracle A, right? If there is a proof that shows that P is not equal to NP using a diagonalization, then that should also relativize, meaning it should extend to the statement that P to the A is not equal to NP to the A for any oracle A, right? For any oracle A. So this is what if there was a way to settle P versus NP using diagonalization, then the same statement should hold good even with oracles. And what Baker, Gill and Soloway showed in 1975 is that P versus NP cannot be resolved using diagonalization. In either way, P equal to NP is also not possible, P not equal to NP is also not possible. How did they do that? They showed two oracles, A and B, such that with respect to A, P to the A is equal to NP to the A, and P to the B is not equal to NP to the B. So if someone showed, anyway it's written above, if somebody showed that P is not equal to NP using diagonalization, then you should be able to relativize, meaning P to the A will be not equal to NP to the A for all oracles, right? But here we have an oracle that shows that P to the A is equal to NP to the A. We have an oracle where P to the A is equal to NP to the A. So that rules out a proof of P not equal to NP using diagonalization. Similarly, if there is a proof for P equal to NP using diagonalization, right, then that should also relativize, meaning it should extend to PB equal to NP to the B for all oracles B. However, Baker, Gill and Soloway showed another oracle B such that PB is not equal to NP to the B. So therefore, you cannot show that P equal to NP using diagonalization as well. So you cannot solve it P equal to NP, you also cannot solve P not equal to NP using diagonalization. Hence, you cannot settle P versus NP using diagonalization. This was the result of Baker, Gill and Soloway. Right? So basically they told people don't even try diagonalization in an attempt to solve P versus NP. Such diagonalization alone is not going to be enough because of this. Right? So it's very, very interesting, right? So it is not a proof that P equal to NP, it's not a proof that P not equal to NP, it is a proof that shows that a certain technique to resolve the problem will not work, right? So it like many, as I have said before, many complexity theorists have spent a lot of time and effort, and that too very intelligent people have spent a lot of time on the P versus NP question. So even this kind of an input, right? Don't try this approach. Even that is helpful. But this is not just some random statement, don't try this approach. It's actually a statement backed up with a perfectly logical and correct proof that if you try this, you will not succeed because of this and this reasons, right? So that way it's very interesting result, right? Perhaps the first result of this type, this proof attempt or this proof approach or this proof technique does not work, right? So let's see the first part of the proof first, which is an oracle A such that P to the A is equal to NP to the A, right? So the basic idea is to make A. So you want an oracle such that, so we don't know what P and NP, how they relate, right? It may be equal, it may be a proper subset. Okay, so now what kind of A will make P to the A equal to NP to the A? So the idea is to make A very powerful, right? You make it so powerful that it doesn't matter what kind of base machine is asking queries. So even if one has non-determinism, one does not, even then the oracle is so powerful that it doesn't really matter if the base machine had non-determinism or not, right? So that is the idea. So to make A very powerful, right? So the language that I am describing is something that runs in exponential time, okay? So what is exp time? So the complexity class exp time, or sometimes denoted exp, I have not defined this before in this course, is the union of all d time 2 power n power k, right? So if I had d time n power k, it would be polynomial time. 2 power n power k means it's the exponent is polynomial, so it's exponential time, right? So this is exp, right? So this is exp, and the language and the oracle or the language A is mx 1 power n. Okay, 1 power n just means n ones. So where m is a description of a Turing machine, x is description is some string, and 1 power n is, well, just n ones. And what is the language? The set of all such three tuples where m outputs 1, or maybe you could say m accepts on x, given on x within 2 power n steps, right? So where 2 power n steps is the number of steps, and that is given by 1 power n. 1 power n meaning you are given n in unary, right? So this is just 1 power n is nothing but n in unary, right? So you are given n in unary, and the language is that m should output 1 on the input x within 2 power n steps. Okay, m should output 1 on x within 2 power n steps. And first of all, notice that this language is in exponential time. Why is that? Because we could simulate m for 2 power n steps on x, right? On the input x for 2 power n steps. So it may take maybe roughly order 2 power n steps, maybe 2 power n multiplied by some constant or something like that. And right? So and the input length, right? Input length is bigger than n, right? So the input length is the entire is basically equal to the size of the description of m, right, plus length of x plus n. So this is certainly bigger than n, or at least n, and it runs in 2 power n steps. So which means that the running time is 2 power n, which is less than exponential time, or at most exponential time, right? So but in 2 power n steps, so whether it outputs 1 or not, we can decide, and then we can simulate and respond, right? So A itself is in exponential time. Okay, now what we will show is that P power A, or P to the A, and NP to the A are both equal to exp. Okay, let's see why. So first of all, we will show that exp is contained in P to the A. So as I have said in the previous lecture, we take an arbitrary, so whenever we have a containment like this to show, we take an arbitrary language from the left hand side and show that this belongs to the right hand side. So let L be in an arbitrary language in exp time. Okay, which means there is a exp time decider for L. So let that decider be M, and let M run in 2 power n power k time, right? This is what exp time was. 2 power n power k should be the running time complexity, right? So n be the so basically it runs in, it's also deterministic time, right? Not deterministic, because it's in p to, it is in exp time, right? And to decide L in p to the a, right? Again, this is p to the a, right? So which means it's a polynomial time machine that has the language a as an oracle. So we can ask questions of the form m x 1 power n, right? So what we can do, so whether m runs, okay, we know m runs in 2 power n power k time. So we can just give it, we can just ask the oracle, does it give the right answer in 2 power n power k time? So to ask this, you need to ask, give n power k in unary, that is n power k once you have to give, and the description of the Turing machine M and the input x. So to decide whether x is in L or not, we give m comma x comma 1 power n power k, which is just n power k in unary, to the oracle, right? So if m accepts x in 2 power n power k time, then the oracle will respond yes, otherwise it will respond no, and that's it. So and what does the p to the a machine actually, the base machine have to do? The base machine just has to just write down this 1 m x 1 power n power k in the tape, in the query tape, and this can certainly be done in polynomial time, right? Because yeah, n power k is what it has to write, and m and x are fixed. X is the input, right? So this can be done, right? Hence, so so where in fact this is actually a many one reduction, right? So this is actually a many one reduction. Why? Because it's like to decide whether x is in L, you are just making a call to the A oracle with the help of a polynomial time running machine, right? So we just make one query. So it's a many one reduction as well, right? You can view it as a many one reduction. So an arbitrary language in exp time is contained in a machine, that a p to the a machine. Second part is to show that np to the a is contained in exp time. Okay, so this is slightly more involved. Let's see the proof. So let n be the np machine, right? So there is np to the a, right? So the base machine be n. Suppose, so it's an np machine, so it runs in polynomial time, not deterministic polynomial time. Suppose the running time is n power k. Now, as you may recall, right? So when you have a non-deterministic machine, there are several possible computation paths, right? And then, right? So this is how the structure looks like. What is the number of computation paths? We do not know, but let B be the branching factor. In this figure, I think 4 is the maximum branching factor. If the max branching factor is B, which means the number of children in this computation tree, maximum number of children for any node in this computation tree, then it can have at most B power height, and the height is the time taken, and in which in this case is n power k. So B power height is B power n power k computation paths, right? And it has that many computation paths, which means B power n power k can also be written as 2 power log B multiplied by n power k, right? So that many computation paths are there, right? So all that we need to show that this is contained in exp, right? So consider some language in np to the a that has to be shown to be contained in exp, right? So now there is an np machine which has at most 2 power log b times n power k, which is an exponential quantity, and we could use the exp time machine to just run each or go through each of these paths, right? So there are that b power n power k paths and each of length n power k. So it is exp time, it is upper bounded by exp time, right? The only thing is that it is not simply an NP machine, but it is also an NP machine with a oracle, right? So now it may encounter, let's say at this particular point, it may say now query A, right? So it is just not just a matter of counting down each computation paths. It may say query A, it may say query A, many places, right? So these queries also have to be performed, but the exp machine doesn't have access to any oracle, which means it has to actually run the decider for A, or maybe check for the membership in A by its own means. But as we have already seen, the language A itself is in exp, right? So as we have already seen, A itself is in exp. So when there is a need to query A, what can be done by the exp time machine is to simply run the exponential time algorithm for A and then output the answer, and then the exp time machine can continue the simulation of the non-deterministic machine. So all that one does, or the exp time machine does, is to run through each of these paths in the computation tree, and we know there are at most exponentially many paths, in fact 2 power log b multiplied by n power k, and you may encounter the A queries, but when you encounter the A queries, all that one has to do is to run the exp time decider, which is also okay. So and that will be another exponential quantity, the time taken for that, but multiplication of 2 exponential quantities is also okay. That will also be another exponential time quantity. So whenever now n can be simulated by an exp time machine, maybe let's call it E. So it can run through each computation path, and whenever there is an A oracle call, right, each computation path, and then whenever there is an oracle call to A, then E can simulate the A decider, right? I have written simulate A, so I meant decider for A as well, since A is itself in exp time. Thus, E can simulate n power A in exponential time. This means that n power A, an arbitrary language in n power A, sorry, not n power A, n power A, right? So an arbitrary language in np power A is contained in exp, right? So we have shown first that exp is contained in polynomial p to the A, then we have shown that np to the A is in exp, right? And finally we have this connection also, simply because p is a subset of np, so p to the A will also be a subset of np to the A, right? Whether it is a strict subset or not, we do not know, but we don't need to know that, because we have a chain of containments, right? Exp contained in p to the A, contained in np to the A, contained in exp. So we have a chain of containments where the left hand side and the right hand side are the same, right? So what if, just to understand, what if you had a chain of inequalities like which says that 3 is less than or equal to x, just in terms of numbers, right? Less than or equal to x, less than or equal to y, less than or equal to 3. There is only one way to make all this true. The one way is that x and y are both equal to 3. Similarly, there is only one way to make all this true. It is that p power A and np power A are equal and equal to exp. Hence, p power A equal to np power A, which is what we wanted. We wanted an oracle A such that p power A equal to np power A. And again, just to remind you, this rules out any oracle, any proof of that shows that P not equal to NP using diagonalization. I'll just summarize very quickly. The idea is to we have to show P power A equal to NP power A. The idea is to make A powerful so that the base machine does not the limitations of the base machine does not come into picture. First of all, exponential time is contained in P power A because you could just simply query A once and get the answer. And NP power A is contained in exponential time because you could simply run through all the computation paths in exponential time. And whenever there is an A oracle query, that query also can be performed in exponential time. Hence, NP power A is contained in exponential time. And obviously, P power A is contained in NP power A because it's a subclass. Hence, it follows that NP power A equal to P power A. There's one more thing I just wanted to say is that instead of so here we had an X time language A, right? X time oracle A. Another thing that works is a P-space complete language like TQBF, right? TQBF also works. And the proof outline is pretty much the same. So you could show that NP power TQBF is contained in P-space and P-space is contained in P power TQBF. And then finally we have the sandwich equation. P-space is contained in P power TQBF contained in NP power TQBF contained in P-space again. So it has to be the case that P power TQBF equal to NP power TQBF. So A equal to TQBF also works